All right, so we're going to begin Chapter 5 now, and Chapter 5 is all about trigonometric identities. Now, we've seen a few identities so far, and in fact, the family of identities that we've seen are referred to as the fundamental identities. So this section 5.1 recaps those identities, and we're going to play around with them a little. But the main focus of Chapter 5 is twofold. One is that we're going to reveal many more trigonometric identities that themselves are very useful and important to know and know how to use. And the other thing that we're going to see is, in a broader sense, is how to do algebra with trigonometric functions. So we're really putting a focus now on the trig functions as mathematical objects. So how can we do things that we're used to doing with algebra, like foiling or factoring, or reducing complex fractions, etc. And, well, all of those rules, of course, work for any function in math, but specifically the trigonometric functions with all these different identities, we get really powerful techniques that aren't available to us when we're just working with like x and y out in the regular math world. So let's recall the fundamental identities, and they themselves are in categories. So let's start with the really most basic ones, which we know, which are the reciprocal identities. And those are basically the fact that cosecant of theta is 1 divided by sine of theta. We saw that really early on this semester. Secant of theta, of course, is 1 over cosine of theta. And cotangent of theta is, of course, 1 over tangent of theta. So these are the principal reciprocal identities. And I really want to start stressing here that identities don't always come packaged perfectly in one of these formats. For instance, we could take this identity right here, and by multiplying both left and right side by tangent of theta, we could get tangent of theta times cotangent of theta is equal to 1. Okay, so that's a trigonometric identity in its own right, which means if you're doing any kind of algebra and you have a term that's tangent times cotangent, you get to immediately just replace that term with 1. Okay, taking that a step further, if you divide both sides of that by cotangent, then on the left you'll just get tangent of theta is 1 over cotangent of theta, which of course we already knew that, but it's just another way of articulating this identity right here. So just be aware that identities can be written many different ways, and they can show up many different ways. Okay, another category of identities that we saw were the quotient identities. And there were two of those. There was, of course, this one, tangent of theta is sine of theta divided by cosine of theta. And cotangent of theta is cosine of theta divided by sine of theta. All right, and finally, the other main category that we saw were the Pythagorean identities. And there were 3 of them. So there's, of course, the main one, which is cosine squared theta plus sine squared theta is equal to 1. And you really need to just know that one instantly by looking at it. But then there were 2 other ones that were similar to them. And for instance, if we divided both sides by cosine squared, we would get 1 plus sine squared over cosine squared, which is tangent squared. 1 divided by cosine squared, which would be secant squared. Okay, and this guy, of course, had an associated mnemonic, I tan secretly. Returning to this identity, if we instead divided both sides by sine squared of theta, we'd get sine squared of theta divided by sine squared theta, which is 1, plus cosine squared divided by sine squared, which is cotangent squared. And on the right, 1 divided by sine squared, which is cosecant squared. And the mnemonic for this one was 1 coat in the closet. Now, once again, these also come in different forms. So for instance, we could write sine squared as 1 minus cosine squared, right? Or negating both sides, negative sine squared as cosine squared theta minus 1. So again, like I said earlier, it's just a really good idea in general to start to recognize that identities might come in slightly varied forms and to look for those forms so that you could use the slight variant version of an identity. Okay, and also we recently saw the negative angle identities. These emerged when we investigated the symmetry of the graphs of sine, cosine, and tangent, and those are as follows. We had sine of negative an angle is negative sine of the angle, and tangent had the same property. Tangent of negative an angle is negative tangent of an angle. On the other hand, cosine of negative an angle is the same thing as cosine of positive an angle. So you can just throw away the negative for cosine. All right, so collectively, this entire set of identities are regarded as the fundamental identities. All right, so we are interested in finding sine of theta, and we're given cosine of negative theta, and we're also told that cotangent of theta is negative. So first of all, we have two angles in this problem. We have theta, but also we have negative theta, right? And these are actually different angles. So the first thing we should do is get everything down to one angle, which means what is cosine of theta if cosine of negative theta is rad 3 over 6? Well, since cosine of negative theta is equal to cosine of theta, and cosine of negative theta was given to be rad 3 over 6, well, then cosine of positive theta is also rad 3 over 6. So we can now just pretend like we were given the fact that cosine of positive theta is rad 3 over 6, and we don't have to worry about negative theta for the rest of this problem. Okay, so the next thing we should determine is the quadrant of theta. So what were we given? Well, we were given that cotangent of theta is negative, and we were given that cosine of theta, or we deduced that cosine of theta is rad 3 over 6, which is positive. So that is cosine of theta is positive. So what quadrant has a negative cotangent value and a positive cosine value? So this must be that theta is in the fourth quadrant. And since we're interested in sine of theta, and we know theta is in the fourth quadrant, we know in advance that sine of theta will be negative. Okay, so here we have, of course, cosine of theta, and we're interested in sine of theta. So we're going to need an identity that relates sine and cosine. Of course, that's a Pythagorean identity. So let's just solve this identity for sine of theta. So sine squared of theta is 1 minus cosine squared of theta. So this means sine squared theta is 1 minus, well, cosine squared means the square of cosine theta. And cosine of theta was given as rad 3 over 6. So that's what's being squared. Okay, so when we square rad 3, that gives us 3. And when we square 6, we get 36. So this is 1 minus 1 over 12. So this is like 12 over 12 minus 1 over 12, which is 11 over 12. So where did we leave off? We're at sine squared theta is equal to 11 over 12. So now we just need to take the square root of both sides. And we also can't leave this as a plus or minus. We need to actually decide, but we're going to choose, of course, the negative because we know sine is negative. and that's because we're in quadrant 4. So, okay, well, where are we here? We're sine of theta is negative of rad 11 divided by rad 12 by distributing the radical into the fraction. And rad 12 reduces as a radical to 2 rad 3. And this rationalizes. So rad 11 times rad 3 is rad 33, and the denominator will be 2 times 3, which is 6. So our conclusion is that sine of theta is negative rad 33 over 6. All right, now it's perfectly reasonable if you're looking at everything that we did and thinking, wow, we could have solved this using a right triangle with way less writing, and you're absolutely right. However, throughout Chapter 5, we're going to see problems of this nature, where we're given a little bit of information, like cosine or sine of an angle, and we're asked to find some other trig function of an angle, and triangles are not necessarily going to be an appropriate way of solving that, namely because we will have sometimes more than one angle in the problem. And simply put, you can't use a triangle in that case. So you have no choice but to use an identity. So I strongly recommend that you start now getting used to using identities to solve this kind of problem. For this specific question, absolutely, a triangle would have worked, and it would have probably been shorter and more compact. And in fact, just to remind you of that method, since it is all important, let's quickly solve this problem again using just a triangle. Okay, so here's the problem posed exactly as it was earlier, and we'll put redo with a triangle. Okay, so from our earlier preliminary analysis, we determined that cosine of theta was rad 3 over 6, so we threw away the negative because cosine of negative theta is cosine of theta, and that theta is in quad 4. So that means that we know sine of theta will be negative. Okay, so let's just draw a triangle. And we'll drop our theta on here. So we know that cosine of theta is rad 3 over 6. Now, cosine concerns adjacent over hypotenuse. So we're going to just label this adjacent side as rad 3 and the hypotenuse as 6. Okay. This missing side here is, let's call it A. And we can see that by the Pythagorean theorem, a squared plus b squared is equal to c squared. So that's a squared plus b squared, well, b is the base, and that's the square of rad 3, is equal to c squared, the hypotenuse, which is the square of 6. So we have a squared plus 3 is equal to 36, and therefore a squared is equal to 36 minus 3, which is 33. So a is equal to rad 33. Remember, there's no plus or minus in this context because on a triangle, all lengths are always positive. So now that we know that this length here is rad 33, we can in fact read sine, cosine, tangent, whatever off of this triangle. We just have to remember to manually assign a plus or minus based on the quadrant of theta. So we can see that sine of theta, which is what we're after, which we know to be negative because theta is in quad 4, and sine concerns the opposite side over the hypotenuse. So this will be rad 33 over 6. All right, so this is our first example of actually looking at a trigonometric expression just in and of itself and seeing, hey, can we simplify this? And now, in order to do that, you have every tool you've ever learned from algebra at your disposal, right? So you can factor, you can FOIL, you can multiply the top and bottom by whatever you want to get something interesting to happen anytime you need to. You can cancel factors, you can do whatever, right? As long as it's legal algebraically. But you also have all the trigonometry you've learned, meaning all the trigonometric identities specifically. Now, this doesn't just say simplify, it says simplify by writing in terms of sine and cosine. And this is acknowledging a fact that every single trig function, of the 6, of course, can be very easily written in terms of just sine and cosine. For instance, tangent is sine divided by cosine. And secant is 1 divided by cosine. So the fact that every single function can be easily written in terms of sine and cosine means that if we were to go and take a complicated expression like this and replace everything with its sine and cosine version of itself, then we might see things that are going to start to cancel that weren't obvious before. So here's the original. And now let's replace tangent with sine over cosine, which means that tangent squared is sine squared divided by cosine squared. And secant squared is 1 divided by cosine squared. Now, the problem we have here is this is called a complex fraction, where you have a fraction within a fraction. This is going to happen all the time with trigonometric expressions because of the fact that so many trig functions can be written in terms of sine and cosine this way. So there are several ways you can manage this, but I'm going to strongly encourage one way in particular, which is robust and will handle all these cases. And that is by taking the common denominator among these little denominators. So in this case, that would be cosine squared, and multiplying the entire fraction by cosine squared over cosine squared. So we're multiplying everything by 1, of course. But it's like every single independent term in this fraction is getting multiplied by cosine squared. So we have cosine squared times 1, which is cosine squared. We have cosine squared times this fraction. Well, here the cosine squareds will cancel, leaving us with sine squared. On the bottom, we have cosine squared times 1, which is cosine squared. And here we have cosine squared times 1 over cosine squared. Again, the cosine squareds cancel, and you get 1. Okay, so now let's continue to put our attention on this expression. Oh, look, the numerator is cosine squared plus sine squared, so that's just 1. All right, well, does anything happen to the denominator? Well, again, by the same Pythagorean theorem, we know that cosine squared and 1 are related to each other. So we might guess that this bottom here is sine squared or negative sine squared or something like that, but we don't really want to guess, we want to be correct. So in order to be correct, let's write down cosine squared plus sine squared equals 1, because we know that's true. And this is side work here. And what we're going to do is we're going to create the form of cosine squared minus 1. So we can do that by kind of moving the sine squared over and the 1 over, and we would get cosine squared theta minus 1 is equal to negative sine squared theta. Okay, so that tells us that this denominator is actually equal to negative sine squared theta. So this is 1 over negative sine squared theta. And that's actually equal to negative cosecant squared theta. And that's pretty simple. I don't think we're going to be able to make that any simpler than it is. So let's leave that alone and consider this simplified. All right, let's take one more look at this example. And this time let's simplify it a different way. Because I really want to stress that there are many, many ways you can do things in trigonometry. And I encourage you just to sort of follow your nose. Take a look at what you're working with and follow your thought process. So another thing to try And if you notice this in the last problem, well done. And that is that the numerator here is actually just secant squared. So let's note that 1 plus tangent squared of theta is secant squared of theta. So we can replace the numerator with secant squared. So here's the original problem. And that's just secant squared of theta over 1 minus secant squared of theta. So can we do anything with this denominator? Well, yeah, actually, it looks like the same identity we just used probably works on this denominator. So let's write it down again. 1 plus tan squared theta equals secant squared theta, right? I tan secretly. And again, let's construct exactly what we have. What we have is 1 minus secant squared here. So we could get that by moving the secant squared over, which would give us 1 minus secant squared, and moving the tangent squared over. So we would get 1 minus secant squared theta is negative tangent squared theta. Okay, so this is secant squared theta divided by negative tangent squared theta. All right, so we're on our way here to simplifying this. Now, at this point, perhaps you might want to turn everything in terms of sine and cosine to see exactly what's going to cancel, if anything. So secant squared is 1 over cosine squared, and tangent squared is sine squared over cosine squared. Okay, so again, if you multiply this by cosine squared over cosine squared, you're going to get cancellation right away. And you'll see that this is negative 1 over sine squared of theta, which is negative cosecant squared of theta. Of course, that's the same answer that we got earlier because math always wins. Okay, let's simplify this one here. Now, to be honest, it's not even obvious that this isn't already simplified all the way down. But there's no real harm in playing with this. So looking at what we have, there's really no obvious algebraic moves that we can do, but what we can do is write everything in terms of sine and cosine and seeing if something becomes apparent at that point. And we know that cosecant is 1 over sine of theta. So we can write this as 1 over sine of theta minus sine of theta. And that's because cosecant of theta is 1 over sine of theta. Okay, so we seem to have made it a little bit worse than what we started with. However, it's now apparent that both terms have a sine of theta. And in fact, if we can get both terms to have the same denominator, then we can add these two expressions together via common denominator. So what we should do is multiply the sine of theta by sine of theta over sine of theta. So we now have 1 over sine of theta minus sine squared theta over sine of theta. And because we have a common denominator, we can write 1 minus sine squared theta over that common denominator of sine theta. Okay, excellent. And hopefully you're looking at 1 minus sine squared theta and thinking, hey, that's a thing. That's cosine squared theta. All right, now what if you don't see that right away? Well, hopefully at least you recognize that 1 minus sine squared theta is some version of cosine squared. It's sort of kind of a variant on the main Pythagorean identity. So if you're not quite sure, you can write down the main Pythagorean identity as we understand it and just construct 1 minus sine squared theta, which of course that would just involve moving this one term over. So we have cosine squared is 1 minus sine squared. And there you are. There you can see 1 minus sine squared is cosine squared. Okay, so Well, what do we have here? Cosine squared theta over sine of theta. Well, we know that cosine over sine, if the cosine's not squared, is cotangent. But we do have a cosine squared, so we can't just write this as cotangent, and it's certainly not cotangent squared, because cotangent squared would be cosine squared over sine squared. So cosine squared in the numerator just means cosine times cosine. So we could simply write this as cosine of theta times cosine of theta divided by sine of theta. And cosine of theta divided by sine of theta is cotangent. So this can be cosine of theta times cotangent of theta. And that's actually as simple as this thing's going to get. It's a little subjective that we started with cosecant of theta minus sine of theta and, quote, simplified it, unquote, to cosine of theta times cotangent of theta. It's just two trig functions that we started with and two trig functions that we ended with. But it is what it is, and it's a little simpler because at least it's only one term now instead of two terms. All right, so for our last example, let's simplify this thing. So again, I want to stress you have every tool from mathematics that you know and love at your disposal. And I hope you're looking at this thing and thinking, you know, maybe we should FOIL this. We have a binomial times a binomial. So I absolutely agree. FOILing is the right way to approach this. So here's where we started. Sine of theta minus cosine of theta times cosecant of theta plus secant of theta. So let's FOIL. So we're going to have sine of theta times cosecant of theta, and then sine of theta times secant of theta, and then negative cosine of theta times cosecant of theta, and then finally minus cosine of theta times secant of theta. All right. Don't forget that when you're working with these, you need a theta, or whatever the argument is. Many times it's an x or a t, every time you write a trig function. So don't just write sine, cosecant, plus sine, secant, etc. That's horrible. Wrong. You need that argument, which is the variable. Okay, so now what is sine times cosecant? Well, sine and cosecant are reciprocals, so this is just going to be 1. Okay, well, what's sine times secant? Well, secant is 1 over cosine. So perhaps we write that as sine over cosine. It'll become more evident what that really is. Well, that's tangent, okay, but we'll write that on the next round. So what's cosine cosecant? Well, cosine of theta is cosine of theta, but cosecant of theta is 1 over sine of theta. So we have cosine of theta over sine of theta, which we know is going to turn into cotangent of theta. All right, we'll do that on the next round. And cosine of theta times secant of theta, well, that's 1. Again, because those are reciprocals. All right, so, well, we certainly can see that we have 1 minus 1, which will cancel, so the 1's will go away. We have sine of theta over cosine of theta, which is tangent of theta, and cosine of theta over sine of theta, which is cotangent of theta. All right, so that's about as simple as we can make it. Certainly a lot simpler than what we started with.